Alright, this is a heat transfer problem, and we're dealing with a flat plate that has a width of 1 meters and a length of 0.2 meters. Its surface temperature is kept at 32 degrees Celsius. We have a fluid going over it. We're gonna deal with only on the top part of it. Our fluid is water. The temperature of the water is 22 degrees Celsius. We also know the velocity of the fluid, 0.5 meters per second. They want us to find the average heat transfer coefficient, the heat transfer rate, and the drag force on the plate. Alright, so let's get started. On the left side, I'm gonna leave a little space here because we're gonna have to be looking up a bunch of properties from tables, so I'm just gonna mark them right here. So let's think, what kind of situation are we dealing with? This is a heat transfer problem, right? Now there are three main categories in heat transfer: conduction, convection, and radiation. Here we can tell that we are dealing with convection, so conduction and radiation we can cross out. Now what kind of flow are we dealing with? We are not in a tube or a duct, so we can see that we are dealing with external flow, not internal flow. I'm gonna cross it out. Now let's consider the geometry. What kind of geometry are we dealing with? Is it a flat plate or is it a blunt body? We are dealing with a blunt body, so sorry, the other way. We are crossing out the blunt body because we are dealing with a flat plate. Now, we are not dealing with a constant flux situation, and they are telling us that the surface temperature is at a constant 32 degrees. So, we are dealing with a constant surface temperature situation. There you go. Constant flux is crossed out. And now the last setup, what are we dealing with? Is this a laminar flow or is it a turbulent or maybe even a mixed flow? At this point, we don't know. We can't tell. So, we're gonna have to find that out. So all this is good to know because we're gonna have to select out which kind of formulas do we work with. And as we know, in this heat transfer situation, we have a lot of formulas to deal with. If you make yourself a cheat sheet, would be very helpful. But if you logisticize out like this, you can find out much easier what kind of group of formulas are you gonna be relying on. So let's find out, are we laminar or turbulent? We're gonna look at the Reynolds number for that. First of all, we're gonna consider our critical Reynolds number at 5 times 10 to the 5th. Then, here are the two formulas that we could consider for our Reynolds number. I'm gonna pick this one, the velocity times length over kinematic viscosity. Here we do not know kinematic viscosity, which is a property. Therefore, we're gonna have to look it up in tables. But first, all these formulas that we got to, which are external flow, flat plate, isothermal surface, we're gonna come here laminar, turbulent, or mixed. Now from these, doesn't really matter which situation are we gonna end up in, because all of these are requiring us to take properties from tables based on the film temperature. So in order to get our properties, we're gonna have to find film temperature first. Right here, our film temperature, 22 degrees plus 32 divided by 2, it gives us 27 Celsius. Well, let's convert it to Kelvin since all our tables are in Kelvin, and we have 300 Kelvin. This is very good because most tables will have this number and we don't have to interpolate for it. There it is, our kinematic viscosity. Now we have everything that we need. We can go ahead and plug in to our formula for Reynolds number, and we can find that our Reynolds number is 1.17 10 to the 5th. Now compare it to the critical, it is smaller. Therefore, this gives us that we are in a laminar flow situation. Therefore, when you select your formulas, make sure you select from the laminar part, not turbulent or mixed, laminar. The first question was the average heat transfer coefficient, so we're gonna select our formula from the correlations right here. From here we're gonna go ahead and solve for our coefficient that we're looking for. There it is. Now let's see, do we have everything or not? Right off the bat, K we don't have it, and X we have it, RE we have it, and the Prandtl number we don't have it. So we have two properties that we have to go to tables and look it up. Again, at 300 degrees Kelvin, K and Prandtl number, we find them. Now we can go ahead, plug them in to our formula, and we can find our average heat transfer coefficient right here, 1251.2. One point that I should emphasize, make sure that you select the correct formula, because we have formulas for local and we have formulas for average setup. The local would just give you at a certain point on the plate what you're looking for. The average is for the whole plate. Now our next question is the heat transfer rate, and they want us to find only for the top. We are not worried about both sides, just the top. There's a formula, heat transfer rate equals the flux times area. For the flux, we're gonna write up the H times Ts minus T infinite. This is our flux formula for convection, and then times the area. Right here, heat transfer rate equals H times the area. I'm gonna break it up, length times width. What we have up here, Ts minus T infinite. We have everything we need. For this, we would need our average coefficient, right? For the whole plate, we don't want a coefficient for just one location. There you go, we have everything, we can plug it in, and we are able to find that our heat rate is 2502 watts. Let me box these two answers since they are our answers. There you go. Now, third, drag force. We want us to find the drag force on the plate. Now to start off, we're gonna use a formula from strength of materials, and which is the stress, shear force, shear stress equals force over area. In our case, the force is this one, the drag force, over the area. Now if we would be considering both sides of the plate, then we would put here 2 times A. But they asked us only to consider one side, so therefore just A will do it. We're gonna solve for our drag force, which is equal to tau times A. Now, here the area we know, but the tau we do not. To go around this, we're gonna use one of the correlations from our heat transfer, which is the friction coefficient equals tau over 1/2 rho u squared equals 1.328 Reynolds number on the -1/2. From here, we're gonna solve for our tau. We're gonna use only these two sides. There it is. Now we know our tau, and in this setup, we know this one. We're gonna have to find our density, and we know the velocity. We're gonna take this, plug it in right here. And area we know, so we only need to find is our density. We're gonna go to our tables, find our density. We can go back here, plug in everything, and we can find our drag force to be 0.0967 newtons.